You don't have too much philosophy to think about the ingredients of a cake. For a cake or any human-made object, it is straightforward. You just need to decompose it into what it is made of. But when you ask the question about nature-made object, like a tree, not only decomposing it, but you also have to go to a smaller and smaller scale. But today we are going to talk about the story of the electron, the basic ingredient of atom. The 19th century was a golden age to play around with electricity and to apply it to different materials to see what's inside of them. One of the examples is the gas discharge, which is the foundation of the neon lamp. If you apply electricity to a gas, it starts to shine. But they didn't know what is the cause of it, because they didn't know about the atoms. So this phenomenon was well observed, but there was no explanation of why it is happening. The phenomenon of the gas discharge was observed by other physicists, but it was Heinrich Geissler who systematically studied it. Nowadays we know that it is because of the ionization of the electrons inside of the atoms, but the actual surprise was in the cathode rays. The discovery of cathode ray by William Crookes and John Heathorp was the initial step towards uncovering the electron. At the time of discovery, there were a few questions about cathode rays. Are they electromagnetic waves or stream of particles? Do they carry electric charge or they are neutral? Do they carry any momentum? Are they discrete particles or they are like a continuous liquid? A few people worked on those questions. One of them was Philip Lenard, a Nobel Prize winner in 1905. His experiments demonstrated that cathode rays could penetrate thin metal foils, a feat difficult for electromagnetic waves because conductors typically block such waves. And he also observed that cathode rays are deflected by the thin metal foils, which might lead into the conclusion that there are Coulombic interaction between cathode rays and the metal, which cannot be true for the electromagnetic wave. But most of these questions were answered by Crookes himself. He should also be credited for the X-ray discovery, because his setup was the base tool for the X-ray production later. He also showed that cathode ray can rotate turbine, which means they have momentum. But perhaps the most important observation was that cathode ray is deflected by a magnetic field. That can be an indication that the cathode rays carry electrical charges. But it was up to 1897, 1906 Nobel Prize winner Joseph Thomson assumed if cathode rays are charged particles, how to measure the mass to the charge ratio. Well, at that time it wasn't possible to measure the charge of the particle or the mass of them individually and separately. But the measurement of the mass to charge ratio could have been done with a few experimental techniques that we are going to demonstrate. In his paper published in the Journal of Philosophical Magazine, he mentions that some people believe cathode ray could be explained by the aesthetic theory, which I discussed in the special relativity video. But he explains that himself believes in charged particle theory instead of aesthetic theory. As we said before him, there were so many people who realized that cathode rays carry electric charges, and that charge is negative. He mentions that before him, Perrine measured the charges of the cathode ray using an electroscope, and it was well known that that charge is negative. And he also mentions that if we are using a magnet, the electroscope doesn't show any sign of getting charged. But at the same time, there is no proof that cathode ray and negatively charged particle are the same thing or are a different thing. This is the setup illustrated by Thompson to show the Perrine experiment, where cathode rays are fed into an electroscope to measure their electrical charges. In the 19th century, thermionic emission was observed as the release of particles from a heated material. When the material was sufficiently heated, it emitted these particles, believed to be some form of energy or matter. The exact nature of those particles was not yet understood. In Thompson Experiment, thermionic emission was used to release particles from a heated cathode, creating a stream of those particles known as cathode rays. An anode with a slit allowed a focused stream of those particles to pass through it and hit the phosphorescent material, causing it to glue. In Thomson's first method, he measured the total charge of the emitted cathode rays using an electrometer. He corrected the rays in the vessel connected to the electrometer to determine the total charge. Simultaneously, he used a magnet to deflect the rays, allowing him to measure their radius of curvature. The image shows the equation for W for kinetic energy measured by the current, and the rho and I for the magnetic deflection. By knowing these charges and kinetic energy and the current, he could determine the velocity and calculate the charge to mass ratio. In Thomson's second method, he used the deflection of cathode rays under both electric and magnetic fields. By adjusting the electric field so that the deflection caused by the electric and magnetic fields were equal, he could simplify the calculation by cancelling out one variable. The equations shown in the image, such as theta and phi, illustrates how the angles of deflection are related to electric field F and magnetic field H and the velocity v of one particle. When these deflections are equal, means phi equal to theta, the equations become simple, allowing Thomson to calculate the charge to mass ratio with greater precision. Thomson measured those values for different types of gases in the cathode tubes, as shown in the tables, providing a range of results for various gases like air, hydrogen, and carbonic acid. These measurements confirm the consistency of the charge-to-mass ratio across different gases. Thompson experiment demonstrated that the value of the charge-to-mass ratio is independent of the type of the gas used in the cathode tubes, consistently measuring around 10 to the power of minus 7, which is much smaller than previously known values such as 10 to the power of minus 4 for hydrogen in electrolysis. This revealed that the mass of those particles was 3 orders of magnitude smaller than the hydrogen atom. To continue, the upcoming video will discuss Millikan oil drop experiment, which precisely measured the electron's charge. By combining Thomson's and Millikan results, we are able to accurately determine the mass of the electron. Stay tuned for the Millikan's experiment video.